Hello, everyone. Okay, let's resume with partial charges. So, we haven't really talked about what these mean, but if you recall what a dipole moment is, basically a particle or a compound or a very small object like a particle, like a molecule, right? Um, just think of like the Earth, right? The Earth has a negative pole and a positive pole. Now let's boil that down to a really small size Earth, like a particle, and then we can describe bonds as having one part of the molecule is going to be a charge, and the opposite side is going to be the opposite charge. So it's like the Earth in a sense. Having a north and south pole, a molecule can also have a north and south pole. And we designate north as kind of like positive, south as negative. And so in this case, we denote the area with high electron density as partially negative charge, and then the part of the molecule that has that's less electronegative as the partial positive charge. Okay, so let's take a look at HCl. For chlorine, the electronegativity is 2.87, so that's much larger than that of hydrogen, which is 2.30. So these values, don't worry too much of like how we came to determine these values, but there's a formula, the equation, some mathematics involved where we consider the atom's ionization energy versus and also its tendency to its influence of its positive its nucleus, its positive charge in the atom. So there's some theory behind it, but we are not going to focus on that for this class. Okay. All right. So if there's a difference in electronegativity, right, the electrons in the bond formed between hydrogen and chlorine, they should be attracted to the more partially the more electronegative element, or the element that has more protons and thus a higher effective charge coming from the nucleus, and that's chlorine in this case. So it's to be slightly more attracted to chlorine than to the hydrogen, because hydrogen doesn't have as many protons. Okay, so this would cause a partial charge to build on both atoms with the excess electron density on the chlorine atom. So we can denote this shift in electron density as a delta plus or delta minus. So in actuality here, we will have the actual molecule here, so chlorine and hydrogen here. So just imagine that all the electron density is gathered towards the chlorine atom here. Okay, so that's delta negative. Or towards the more partially positive delta negative. And here, we would put this shaded part as part of the bond. Now it's going to be partially positive here. Okay? Whereas if we were to draw a hydrogen molecule here, the electron density will be shaded in the center and shared equally between the two, because there's no preference for the electrons to be towards one end of the molecule towards the other. So that's kind of how we skew the difference here between, or illustrate the difference between a polar covalent bond and a purely covalent bond. Okay. So if we think about this kind of molecule here, so say we have a hypothetical molecule, AB, okay, AB. If the electronegativity of B is much larger than that of A, which atom, A or B, would have the negative partial charge? Okay, so we know the electronegativity of A is much less than the electronegativity of B. So when we have that case, when this situation occurs, that means A will have the partial positive charge because it's less electronegative, can't hold on to the electrons as much as it wants. So in this case, A will be partially positive and B will be partially negative. So we can actually denote where electron flows in the bond. So it's going to flow in this direction, where the arrow points to where the delta negative is. So that's a dipole moment. Okay. So in this case, atom B will have the partial negative charge. Okay, so now let's talk about the concept of formal charge. Okay? So in this case, formal charge. What is formal charge? So while the actual charge on an atom is actually better represented by a partial charge, it's rather complicated to do for complex molecules. So we devised a system to calculate formal charge. So this kind of helps us picture which atoms are most likely to carry a significant amount of positive or negative charge. So while these, here's a little disclaimer, while these charges are useful, they do not represent the real charges on the atom. It's kind of like I said before, an accounting system. We're just trying to keep track where the electrons go. So if you have a positive charge, that means your electrons around an atom were given to form a bond between another atom. And if you have a negative formal charge, that means around the atom in question, you have more electrons around it than you usually would. So in this way, formal charge is it's as if we, instead of giving electrons away, like in oxidation reduction reactions where we had the oxidation state, okay, this one has a positive charge, this one has a negative charge, because we assume that electrons are transferred between redox reactions. Formal charge is the opposite view of that spectra, or that spectrum. So if oxidation numbers were kind of the ionic view of bonding, formal charge considers the view from the covalent bonding perspective, or from the sharing of electrons. Okay, so it's two different kinds of ways to think about how bonding and transfer of electrons or sharing of electrons is viewed. Okay, so that's one thing we want to keep in mind when we're talking about formal charge. So to calculate formal charge, there's two ways. I'll go over both. There's obviously I will be biased for one way, just because it's easier and it's easier for me to remember. Maybe it'll be easier for some of you too. Okay? So to calculate formal charge, first we divide the electrons in each covalent bond equally between the atoms that form the bond. So now there's some, there's not always a good way to reconcile that, because some elements are electronegative, right? All right. Next, we compare the number of valence electrons that are formally assigned to each atom based on the valence number of electrons, okay? So we compare it to if the element was a neutral atom, okay? So if in my compound, if I had hydrogen, I would compare the number of valence electrons that are assigned to it compared to what hydrogen usually has as a neutral element or a neutral atom of the element. So that might not make sense here right now, but we'll go over it, okay? So if the atom has more valence electrons than a neutral atom, it's going to be a negative charge because it has more. And you have more electrons, right? You're going to be more negatively charged because each electron is negatively charged. Now, if it has fewer electrons, it carries a positive charge because now you're at a deficit. So you have less electrons than you normally would as a neutral element or neutral atom of an element. You're going to have less electrons, and so you'll be more positively charged because now there's more protons. Okay? So let's consider the glycine molecule, an essential amino acid. Okay? So we often write it as H3N plus CH2CO2 minus. Okay? And the minus charge is on one of the oxygen atoms, and the plus charge is on the nitrogen. So let's calculate that. So the general formula for formal charge, I'll provide this on your equation sheet, is formal charge, say, of atom A is equal to the valence electrons of atom A minus the number of electrons of atom A in the compound. So that means the number. So this refers to non-bonding electrons. So first, VA is the number of valence electrons on a neutral atom of an element when it's by itself. Then from that number, you subtract the number of non-bonding electrons on the atom, so atoms in lone pairs, as lone pairs. And then you subtract half the number of electrons involved in bonding, okay? So there's another way to put it. So you could do valence electrons of a neutral element minus the electrons in lone pairs. Okay, so I'll just say number of electrons as lone pairs minus the number of bonds. So the number of bonds refers to how many bonds is that atom involved in, okay? So that's another way to view the formal charge, okay? So remember, this equation on the left might be a little tricky. So another way to think about it is, okay, how many valence electrons does my atom usually have? So you go back to the periodic table, you look at the group number, okay, it's in group 3A. So it must have 3 valence electrons. So you would put 3 for V sub A, okay? But now let's apply this to the molecule in question, glycine, okay? So let's verify that the charge on nitrogen is +1. All right, so we look at nitrogen here. Their nitrogen is in group 5, right? So in this case, VE equals 5. So VE should be 5 valence electrons, right? Okay, so that's what we put down here, 5. Now, are there any non-bonding electrons or lone pairs on the nitrogen atom? No, there's no lone pairs. So we put 0 for N sub N. Okay, 0. Now, how many bonded electrons are there? Well, nitrogen has 2, 4, 6, 8 electrons in bonds. So we put 8 divided by 2 because that tells us how many electrons are shared, so we have to divide that number by 2. So that's why we divided by 2. Or in this case, we can just say, okay, how many bonds is around nitrogen? 4. So 8 divided by 2, 4. 4 bonds, 4. So if we add those numbers up, 5 minus 0 minus 4 gives us +1. So compared to nitrogen as a neutral atom with 5 valence electrons, right? Compared to it when it's now in this compound glycine, it only has 4 valence electrons around it. So now it has a deficit of electrons as it normally would have, so it gets a positive charge. And but compared to the bond it is part of, it's not really going to be partially positive. But we just say, okay, nitrogen has a positive charge, and that's because it has given all of its electrons to form bonds. And when it does that, it's going to be a positive formal charge because it gave up its electron to form an additional bond to a carbon atom. Okay. All right. So the other way to calculate formal charge is like what I said before. Take the valence electrons, subtract the number of lone pairs plus bonds, but there's an even easier way than that. So we need to we need to put formal charges on these elements because they tell us some important properties, like, okay, is my molecule stable? Is it a salt? What can I do with the compound? So it kind of tells us, the distribution of electrons and how that affects some of its electronical properties or its properties as ions. Okay. So the equation for this method is a bit simpler. So I call it the circle or arc method. So you circle the atom in question. You make a circle around it. So you count the number of electrons around the atom in the circle, okay? So we assume the circle is a perfect angle bisector, or is a perfect bisector, and it will divide the electron equally into one electron per atom. So a hydrogen would get one electron, and a nitrogen would get one electron per bond it's involved in. So in this case, nitrogen will get 4 electrons as being part of a bond. Okay? So therefore, now if there's a lone pair on nitrogen, since we circled the nitrogen atom, both of those lone pairs will be involved in nitrogen in the circle, so we count both of them. Okay, so now we take the number we counted as part of the circle, in this case it's 4, and then we simply subtract that from the group number or valence number of electrons on the neutral atom of nitrogen. Okay, so we look at the periodic table, we find that it's in group 5. So for nitrogen, there's 5 valence electrons in a neutral nitrogen atom. Subtract the 4 electrons we got from the circle method, and we get +1. So see the similar technique for determining formal charge, and it gives us the same answer. So you could do this for any compound. So if we do it for oxygen, for example, let's circle oxygen here. All right. So we have 6 electrons from lone pairs because it's part of the circle, right? Plus 1 electron from the bond we bisected. See how we circled the oxygen? We bisect the bond, so that's plus 1 electron. So now let's subtract this number from the valence electrons of oxygen. So remember, oxygen has 6 valence electrons, so 6 valence electrons, minus the 6 plus 7 we just calculated. So 6 plus 1 we just calculated there. That's 6 minus 7 equals -1 charge. And we see on oxygen, it has a -1 charge. So that's how you do it. Okay? But you can also do it the other way. 6 minus 6 electrons from lone pairs or non-bonding electrons. And then -1 for 1 bond around oxygen. So that's still -1. Okay. All right, so now let's calculate the formal charge on each atom in SO2. Okay. Like so? Okay. So let's do some more practice here. So in SO2, remember we had SO2 as a double bond and a single bond for oxygen atoms. Remember, SO2 has 18 valence electrons, like we determined previously. Okay. So this is the structure for sulfur dioxide. Okay. So let's calculate the formal charge on this oxygen atom here. So remember, oxygen has 6 valence electrons minus. Okay, so it has, let's see here, it has 4 non-bonding electrons, right? 4 non-bonding electrons. And then how many bonds are around this oxygen atom? 2. Minus 2. So in this case, this one should be 0 formal charge, and that it is 0. Now let's talk about the sulfur. So let's label this oxygen 1. Right, sulfur is in the same group as oxygen, so the same number of valence electrons here. So 6 minus how many electrons are in lone pairs? How many non-bonding electrons? 2. And then how many bonds is sulfur a part of? 3. So we get 6 minus 2 is 4 minus 3, positive 1. So we can put a plus 1 here. All right. And now for oxygen 2 here, the right-sided oxygen right there. So same kind of deal, 6 electrons. Now it has 6 electrons as non-bonding, as lone pairs, and then 1 bond, and that will give us -1. So these are the formal charges we get for all the atoms in SO2. Okay? All right, so that's how you would calculate the formal charges. So when you draw Lewis structures, you want to be sure you are balancing your charges and making sure that that each atom has the appropriate formal charge based on these calculations. Okay. All right, let's move on now. Okay, so now how do we predict which structure, which structure is the best representation of bonding? Okay, so we can actually determine which structure is the best based on the distribution of formal charge, because they're not all equivalent, right? They're resonance structures, but which one's the best? So if we don't have equivalent resonance structures, we have something called a major and minor contributor. So we are going to go into what makes one a major and minor contributor. Okay, so which one is the best? So this is known as laughing gas. Okay. Yeah, so back in the early days, before there was anesthesia, or coming what we think about anesthesia, the reagents that I used to use were ether, and then before that, or in the history of anesthetics, was laughing gas, which is this molecule right here. So it induces anesthesia, but it also is called that because usually people who are under the influence of this chemical here, they tend to have fits of laughter. So it's actually it causes the reflex, that causes laughter, the laughter response between our brains and our nerves. Yeah, our nerves. Right. Okay. So which structure is actually the best? So the key is to calculate formal charge. So as a general rule, when we draw out Lewis structures or multiple Lewis structures, the best structure is considered to be, the one which we have less formal charges or the smallest formal charges as possible. And we would like the formal charges to be on appropriate atoms. So for example, a negative formal charge should be on the most electronegative atom because that's the most stable configuration for a negative charge. And then the positive charge should be on the least electronegative atom. So those are pretty much the criteria for formal charges and determining which structure is the best. So let's calculate the formal charges for each atom on the three Lewis structures for N2O. Okay, so structure 1. So here we have, so we know the formal charge for nitrogen, right? It's 5 valence electrons, so it's going to be 5 minus, so let's see how many electrons are around it, 2 from non-bonding, and then minus 3 bonds is 0. All right, the second nitrogen is 5 minus 0 electrons from non-bonding, and then 4 from bonding. So that's going to give us a charge of +1. And then oxygen, like we said previously, it's going to be 6 minus 6 minus 1. So that's going to be a -1 charge. And you see here the formal charges, they add up to equal 0. So they must add up to the net charge on the compound or ion. Okay, now let's do structure 2. 5 minus 4 from lone pairs minus 2 from bonding. So this will give us -1 on nitrogen. And then nitrogen into center here is 5 minus 0 minus 4 bonds. So again, +1. And then oxygen here is 6 minus 4 electrons from non-bonding electrons, and then minus 2 for the number of bonds around oxygen. So that will give us 0. Like that. And now lastly for structure 3, we have the first nitrogen, 5 valence electrons minus 6 from bonds. Not 6 electrons from non-bonding electrons, and then -1 for the number of bonds. So this will give us -2. The central nitrogen is again 5 minus 0 minus 4 bonds around nitrogen. So that'll give us +1 again. And lastly, the oxygen on the right there is going to be 6 minus 2 electrons as non-bonding electrons, and then -3 for the number of bonds. So that will give us +1. Yes, +1. Okay. So the structure that has the most charges is going to be the least likely structure for the molecule. So it's going to be considered less. So in this case, we would call this the minor, well, not the minor. So this is not a very good contributor. So structure 3 is not a very good Lewis structure, so it's not going to contribute to much of the structure of laughing gas as much as the other two. So the other two have less charges on the molecule, so that makes it a little bit better. However, one of them is better than the other, and we have to look at where the charges are at. So we have in the first structure a positive charge on nitrogen and then a negative charge on oxygen. So that is a pretty good case for our structure. The second structure, now it has the same kind of charges, but they're on different atoms. And in this case, the 0 is on oxygen, and then the positive charge and negative charge are on nitrogen atoms, both nitrogen atoms. So that's not a very good scenario, because if they're both nitrogen atoms, they should probably not have different formal charges just because they're both nitrogen. So, and since oxygen is more electronegative, it should bear the negative charge. So in this case, structure 2 is not as good as structure 1, and that's because the charges are not on the most appropriate atoms of the right electronegativity. So structure 1 is actually the best. But let's go and summarize our findings here. Okay, structure 1. Let's say, okay, overall good structure. Okay. The reason is that the formal charges are on appropriate atoms. Okay. And it has least number of charges. So the lower number of charges you have, the better. Because charge separation is generally not a good thing to have in the molecule. So you want to limit that as much as you can. All right, structure 2, while it has the least number of charges, least number of charges, oops. But the negative charge okay, is not on the most electronegative atom, which in this case is oxygen. All right. Okay, now what about structure 3? Structure 3 is too many formal charges. Too many okay. And then also negative charge is on nitrogen instead of oxygen. And then if we look above here, what's also bad is that positive charge is on oxygen, where where the positive charge would preferably should be on nitrogen because it's the least electronegative. So those are the critiques there. So structure 2, not as good. Structure 3, the worst. Structure 1, the best. Okay. All right. So in general, we can say, okay, let's see here. So in general, the trend between bond lengths in nitrogen is that a nitrogen-nitrogen single bond is around 146 picometers, a double bond around 125, and then nitrogen triple bond, a nitrogen-nitrogen triple bond is around 110 picometers. So now, an experiment, this nitrogen-nitrogen bond length in N2O gives a result of 113 picometers. So based on this information and based on our analysis of formal charges, which is the most appropriate structure? Okay, so this bond length is consistent with a N triple bond. And this is consistent with structure 1. So here we were able to use formal charge to predict which structure is the best structure for our compound. So not all Lewis structures or resin structures are created equally. So there's always a case where we can use experiment to determine which structure is the major, what we say, structure for the compound. So we could say structure 1 is a major contributor. And then structure 2 is a minor contributor because it's not exactly at 110 picometers. It's slightly greater than. So that kind of tells us, okay, there's some double bonded character as well. So there must be some minor contribution from structure 2. Okay, so let's stop there for today, and we'll pick up in the next lecture going off what we just learned and talking about when to use when to use formal charge and determining how many bonds we should draw around an atom. There'll be some criteria we use, and I'll go over what that is next time. So I'll see everyone in the next video. All right, take care.